part 4 of chapter 3 is combinational circuits. We have designed a circuit that implements a Boolean function, for example, a function f in terms of x, y, and z. The function is defined this way. So this circuit is an example of a combinational circuit. The property of a combinational logic circuit is that the output is determined when the current inputs are applied. So in this example, output of a function f is determined if a current input of x, y, and z are specified. But in later part of this chapter, we are going to study some other case of circuits called the sequential circuits. Sequential circuits where the output is determined not only by the current input but also by the past inputs, which means a history of inputs applied to the current input also determines the current output. So that's called the sequential circuit. One of the popular and important combinational circuit example is a half adder. So half adder is defined as follows. So you have two inputs, x and y, the truth table here, and then it has two outputs. One is a sum and the other is a carry. So this implements adding of two binary digits. So if you have a 0 and the 0 added together, the sum is a 0, but if I have a 1 and 1, if added together, sum is a 0, and then carry is a 1. So we implement this function in hardware such that it has two inputs, x and y, and it produces sum and carry. So if you apply 0 and 0, you have a sum is 0, carry is 0. Truth table is specified this way. 0 and 1 is input here, then sum is a 1, carry 0, 1, 0, sum is a 1, carry is a 0. But if you apply 1 and 1, then sum is 0, and then carry is 1. So that's a truth table of the function we define for this circuit, and that circuit is called half adder. So we can implement this half adder. Let's use a K-map for that. So we have two outputs. So one output is a sum. So what you have is x input, y input, two variable K-map, 0, 1, 0, 1. So sum is 0, 1, 1, 0. So 0, 1, then 1, 0. So sum is this group only one single square only. So this one represent x, y naught, and this one represent x naught, y. So this is a expression for sum, and the expression for carry is it is 1 only if x and y's are 1. So you could use a K-map, or by looking at straight, that is nothing but x and the y 1. So you can design circuit this way. So you have x and y applied there, and that represents carry out. And then for sum, we have two AND gates. One is x and y inverter, and then x inverter not and y. So those two are ORed together. So ORed together here, and that represent sum output. So this is implementation of a half adder. We call this one as a half adder because we don't consider something carry coming from previous days. So if you do multiple bit binary addition, for example 0, 1, 1, 0, and then if you add 1, 0, 1, 1, if you add them, so for this column, this bit position, sum is 1, carry is 0. So you can use this one. However, in next digit, sum is 0 and carry is 1. So carry is 1 there. For this column, you cannot apply this one because it does not take a carry from previous position. So we need to extend this adder to apply something like this situation. We are going to add 2 bits, not only 2, but something coming from previous position, carry. So carry should be taken care. So this circuit should be extended, having one more column was a carry in and then carry out. So we need to have 3 inputs and 2 outputs to fully utilized for this kind of binary number addition. So that is called a full adder. Before we study full adder, here is one observation is that I showed you the design of a half adder in the previous slide, but by looking at the code, truth table, what you find is that sum is when x and y are different, the sum is 1, but they are the same, sum is 0. That is what you have defined in earlier stage, XOR circuit. Another symbol we have that, so we could use XOR gate to implement the half adder directly. But here comes a full adder. So full adder should be as follows. We need to take care of carry in as well. So if x, y's are 0, 0, if carry in is 0, then sum is 0. Carry in is 1, then sum is 1. X, y is 0, 1. Carry in is 0, sum is 1. But there is a carry in, then sum is 0, carry becomes 1. So we have 8 possible cases of input cases, and then carry in is all taken care. Then the circuit would be something like this. You have X input, Y input, and then carry in. And then we have 2 outputs, carry out and then sum. So this module is called a full adder. So let's design full adder circuits for that. So you can use 3 variable K-map. So we have X and then Y and C in. So we have a 3 variable K-map. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And then let's construct a K-map for that. So for some part we have a 0, 1, 1, 0. So 0, 1, 1, 0. Keep in mind that order. 1, 0, 0, 1, 1, 0, 0, 1. That is the order. So this is for sum. So in sum, we have a K-map here, but we find a very interesting pattern. So here is a one group, another group, another group, another group, and so on. So ultimately what you get is it's all independent. There is no adjacent cell at all. So we have some complex expression for that. Each one has individual. So the very first one here is x and then y not c in not plus second one is x not y not c in, and then the 1/3 column x y c in. The last one is x not, this one, y, and then c in not. That's the expression for sum. Now for carry out, so we have another 4 variable K-map, x, y, and c in, 0, 0, 0, 1, 1, 1, 1, 0. So 0, 0, 0, 1, 0, 0, 0, 1, then 0, 1, 1, 1, 0, 1, 1, 1. So grouping, so we have this one, and that one. So we have 3 groupings. All of those are prime implicants, and then all of 3 of those are essential because each has a cell which is not covered by others. So carry out expression is so this group is x does not change, but y changes. So x, y changes and the c in with the value of 1. The horizontal one, x changes, y remains, c in remains. Y remains, c in remains with the value of 1. The last group, x does not change with the value of 1, but y does not change, c in changes. So that's the expression for that. So using those two expressions, we can implement full ladder. So full ladder circuit will be x input, y input, and c in. X, y, and c in. It produces carry out and then sum. And here the circuit is expressed here. You can draw a circuit diagram for each function. Then you implement a full ladder. So once we have a full ladder, we can cascade it like this. So which this implements a binary number addition with like a 16 bit. So we have a bit 16th bit, 15th bit, and so on. So you have x1 and x0. Then another number is again for 16 bits, another number is expressed like this one. Then when you add those two, what you do is add this bit position and then get sum. But if you have a carry, push the carry to the next position, and then with the carry we add those 3 bits, and that becomes sum for this position, and so on. So using full ladder, we can add multiple bits by case cascading full ladder, such that you add x and y with the very least significant bit. The carry in should be 0, and then this bit produces a carry, pass it to the next position, and then add the x and y with the carry. It produces carry and then forward it to the next position, and so on. So if you cascade the full ladders this way, then you can implement multiple bit binary numbers.